Tonight, if you find a dark sky far from city lights, you can see it without any instrument at all. A faint, elongated smudge low in the constellation Andromeda, the single most distant object the human eye can detect unaided. That smudge is a galaxy almost the twin of our own, roughly 2.5 million light-years away, and its light is doing something unusual. Instead of stretching toward red, the way the light from nearly every other galaxy in the universe does, Andromeda's light is compressed toward blue. It is falling toward us at more than 100 kilometers every single second. In roughly 4.5 billion years, current models predict the Milky Way and Andromeda will meet, pass through each other, and slowly merge into a single larger galaxy already nicknamed Milkomeda by the astronomers who study it. What follows is the physics of exactly how two galaxies, each containing hundreds of billions of stars, collide without a single star necessarily touching another. In 1912, at the Lowell Observatory in Arizona, an astronomer named Vesto Slipher pointed a spectrograph at a faint spiral smudge catalogued as the Andromeda Nebula and split its light into a rainbow of wavelengths. He was searching for the object's radial velocity, the speed at which it moved directly toward or away from Earth, measured by how much its light had shifted from where each element's signature lines should sit. What he found surprised him. The Andromeda Nebula's light was shifted toward the blue end of the spectrum, meaning the object was moving toward Earth. At a speed he measured at roughly 300 kilometers per second, it was the first blueshift ever recorded for what would later be understood as another galaxy. Slipher's instrument, a spectrograph attached to the observatory's 24-inch refracting telescope, required exposures lasting many hours, sometimes spread across several nights, to gather enough of Andromeda's faint light to split it into a usable spectrum. He was, at the time, primarily investigating whether spiral nebulae rotated, a separate question from redshift and blueshift entirely, and the discovery of Andromeda's peculiar blueshift arrived partly as a byproduct of that other investigation, a reminder that some of the most consequential findings in astronomy emerge while a careful observer is looking for something else. At the time, nobody knew Andromeda was a galaxy at all. Most astronomers believed it was a nearby cloud of gas and young stars, a smaller structure inside our own Milky Way, which was assumed to be the entire universe. That assumption held for another decade. It took the American astronomer Edwin Hubble, working with the 100-inch telescope at Mount Wilson in California in the 1920s, to resolve individual pulsating stars called Cepheid variables inside Andromeda. Cepheids brighten and dim on a fixed schedule tied directly to their true luminosity, so measuring how bright one appears against how bright it actually is gives a reliable distance. Hubble's measurement placed Andromeda far outside the Milky Way entirely, roughly 2.5 million light-years away by modern calibration. Andromeda was not a nebula inside our galaxy. It was an entire galaxy of its own, one of billions, sitting well beyond our own galaxy's edge. The realization that Andromeda lay beyond the Milky Way arrived in the middle of a wider argument among astronomers of the era, sometimes remembered as the Great Debate, held in 1920 at the Smithsonian in Washington. One side argued the Milky Way was the whole of the universe, and that fuzzy spiral shapes like Andromeda were simply gas clouds within it. The other side argued those spirals were separate island universes entirely, galaxies in their own right, each containing their own billions of stars. Hubble's Cepheid measurement, made just a few years later, settled the argument decisively in favor of the second view. It remains one of the more quietly transformative discoveries in the history of astronomy. Overnight, the known universe grew from one galaxy to an uncountable multitude of them, each one in principle capable of what Andromeda and the Milky Way are now doing to each other. That discovery reframed Slipher's earlier measurement entirely. Over the following decades, as astronomers measured the light of galaxy after galaxy across the sky, an overwhelming pattern emerged. Almost every one of them showed light stretched toward red, not compressed toward blue. Their light was redshifted because the space between those galaxies and our own is expanding, stretching the wavelength of any light crossing it, the way a sound wave stretches as its source moves away. This is the evidence, refined over the following century, that the universe as a whole is expanding, and that the more distant a galaxy is, the faster it appears to recede. Andromeda breaks that pattern. It is one of a small handful of galaxies close enough that the local pull of gravity between it and the Milky Way overpowers the gentle stretch of cosmic expansion at that distance. The two galaxies, along with roughly 100 smaller galaxies, are bound together into a single gravitationally linked structure astronomers call the local group. Inside that group, gravity wins, and Andromeda is not drifting away with the rest of the universe. It is falling toward us. To put a number like 2.5 million light-years in human terms, light leaving Andromeda tonight will not reach Earth for 2.5 million years. Every photon entering a telescope aimed at that smudge left its source before modern humans existed as a species. Yet on the scale of the local group, that gap is close. It is roughly 10 times narrower than the distance to the next nearest large galaxy cluster, which is one reason gravity between the Milky Way and Andromeda can win out over the universe's overall expansion, while more distant galaxies are carried apart faster than gravity can ever pull them back together. A blueshift only tells you that an object is approaching. It says nothing about the angle of approach, whether the object is headed for a direct hit or will sweep past at a distance, the way one car might miss another on an offset course. Slipher's measurement, and every refinement of it made over the following century, could only ever answer half the question. Astronomers would need a second kind of measurement entirely, one that requires watching a galaxy's position shift sideways against the fixed pattern of background stars, something almost too small to detect from any single vantage point in a human lifetime. That second measurement is what would finally tell astronomers whether the Milky Way and Andromeda are truly on a collision course. Picture the Milky Way from directly above its disk, an impossible vantage point no human has ever occupied, and you would see a flattened spiral roughly 100,000 light-years from edge to edge, its arms wound loosely around a dense central bulge like water circling a drain. Scattered through that disk sit somewhere between 100 billion and 400 billion stars, the exact count uncertain because so much of the galaxy's far side is hidden from us behind its own dust and gas. Our Sun sits inside one of the minor spiral arms, roughly 26,000 light-years from the centre, closer to the edge than to the middle, one ordinary star among hundreds of billions of others, doing exactly what it does. Andromeda, viewed the same way, is larger. Its disk stretches across roughly 220,000 light-years, more than double the Milky Way's width, and current estimates put its star count at close to 1 trillion, several times our own galaxy's population, though a large share of Andromeda's stars are fainter, older and more thinly spread than the Milky Way's. Both galaxies share the same basic architecture, a flat rotating disk of stars, gas and dust, a dense central bulge, and a roughly spherical halo of older stars and star clusters surrounding the whole structure like a loose shell. Andromeda has been visible to careful observers for over 1,000 years. The Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars, completed around 964 CE, calling it a small cloud, the earliest known written record of the galaxy that would eventually be understood as an entire second Milky Way beyond our own. The distance separating these two cities of stars, 2.5 million light-years, is difficult to hold in the mind honestly, so it helps to shrink it. Imagine the Milky Way reduced to the size of a dinner plate, about 30 centimeters across. On that scale, the Sun and everything around it, out to the edges of the solar system, would be a mark too small to see with the naked eye, and Andromeda also shrunk given its greater true size to roughly the size of a large serving platter, would sit about 7 meters away, roughly the length of a small room. Two disks of light, each holding the compressed mass of hundreds of billions of stars, separated by a gap that on this scale, a person could walk across in a few seconds. On the true scale, crossing that same gap at the fastest speed any human-made object has ever travelled would take tens of thousands of years. The Sun's own orbit around the Milky Way's centre takes roughly 225 million years to complete a single circuit, a span of time astronomers sometimes call a galactic year. On that calendar, the Sun has completed only about 20 such orbits since it formed, and it will complete only a few more before the Milky Way and Andromeda begin their own long approach. Everything visible in the night sky with the naked eye, every star a person has ever pointed to and named, belongs to this single galactic year, orbiting the same shared centre the Sun does, on a scale so large that the entire history of human civilization amounts to less than 100,000th of a single circuit. Despite containing so much mass, both galaxies are, by volume, almost entirely empty. The stars within them are separated from their nearest neighbours by light-years of open space, distances so large relative to a star's own size that if the Sun were shrunk to the size of an orange, its nearest stellar neighbour, a system called Alpha Centauri, would be another piece of fruit roughly 2,400 kilometers away. A galaxy, despite looking to the eye like a solid pinwheel of light, is closer to a very thin, very wide cloud of scattered points, held together not by any physical contact between its parts, but by something invisible. Both galaxies also travel with retinues of smaller companions. The Milky Way is orbited by dozens of dwarf galaxies, the brightest of which, the Large and Small Magellanic Clouds, are visible to the naked eye from the southern hemisphere as two faint patches of light near the horizon. Andromeda has its own satellites, including two prominent dwarf companions named M32 and M110, visible in long-exposure photographs as small smudges pressed close against Andromeda's outer disk. A third major galaxy, Triangulum, spinning roughly 3 million light-years away, rounds out the trio of large spirals bound into the local group. Whatever happens to the Milky Way and Andromeda over the coming billions of years will likely eventually draw Triangulum and the smaller satellites into the same slow reorganization. Both disks are laced with darker lanes of dust and gas, the raw material of new star formation, glowing faintly pink in long-exposure images wherever radiation from young hot stars ionizes the hydrogen around them. These clouds are where each galaxy is still actively building new stars today, at a combined rate across both galaxies of a few solar masses worth of new stellar material every year. That's something holding hundreds of billions of stars together in a shared orbit around a common center, more than any visible star, planet, or gas cloud, turns out to be doing far more work than the visible galaxy alone can explain. Every galaxy's visible light comes from stars, gas clouds glowing under starlight, and scattered dust. Add up all of that visible material in the Milky Way, and you get a total mass equivalent to somewhere around 200 billion suns. But when astronomers measure how fast our stars near the outer rim of the Milky Way's disk are moving in their orbits, they find speeds that visible mass alone cannot produce. If the galaxy contained only the matter that shines or reflects light, stars at the edge of the disk should be orbiting slowly, the way Neptune orbits the Sun far more slowly than Mercury does, because there is simply less mass pulling on them from that distance. Instead, outer stars orbit at nearly the same speed as stars much closer to the center. The rotation curve, as astronomers call the plot of orbital speed against distance from the center, comes out almost flat, when the visible matter alone predicts it should fall off steeply. The American astronomer Vera Rubin, working with Kent Ford in the 1970s, made exactly this measurement across dozens of spiral galaxies, using the light emitted by hydrogen gas far out in each galaxy's disk to track orbital speeds well beyond where the visible starlight fades. Her results, replicated and refined many times since, became some of the strongest evidence that each galaxy is embedded inside a much larger reservoir of mass that emits no light at all. Astronomers call this material dark matter, a name that describes what it does not do, emit or reflect detectable light, or any electromagnetic radiation rather than what it actually is. Its precise nature remains one of the open questions in physics. Current models predict it may consist of a still undiscovered kind of particle that interacts with ordinary matter almost exclusively through gravity, but no such particle has yet been directly detected in any laboratory. Physicists have proposed several candidate particles that might make up dark matter, including hypothetical particles called WIMPs, short for weakly interacting massive particles, and a separate proposed particle called the axion, though neither has yet been directly detected despite decades of dedicated laboratory searches. Whichever particle, or combination of particles, eventually turns out to be responsible, the gravitational evidence for its existence, from Vera Rubin's original rotation curves to the modern halo estimates used to model the coming Andromeda merger, remains among the most solid results in modern astrophysics, even while the underlying particle physics stays unresolved. Whatever dark matter turns out to be, its gravitational effect is unmistakable, and it is not confined to the visible disk of a galaxy. Estimates place the Milky Way's dark matter halo at roughly 10 times the mass of everything visible combined, stars, gas, and dust together, and that halo extends far beyond the edge of the visible disk, possibly out to somewhere between 300,000 and 600,000 light-years from the galactic center, several times wider than the disk of stars sitting at its middle. Andromeda's halo is thought to be at least as large, plausibly larger given Andromeda's greater total mass. This changes the picture of the coming encounter considerably. When people picture two galaxies colliding, they naturally picture the two disks of visible stars, the parts a photograph actually shows drawing together, but the visible disks are only the bright core of a much larger structure. If both galaxies' dark matter halos genuinely extend several 100,000 light-years from their respective centers, and the two galaxies are separated today by only about 2.5 million light-years and closing, then the outer edges of those two invisible halos may not need billions more years to meet. Some models suggest the halos could already be brushing against each other today, an interaction happening all around us that leaves no visible trace in any photograph, because none of it involves light at all. Confirming this directly is difficult, precisely because dark matter cannot be observed the way starlight can. Astronomers infer the shape and extent of each halo indirectly, from the orbital motion of the smaller satellite galaxies and star clusters trapped within it. The same basic method Vera Rubin used decades ago, applied now at a much larger scale. The picture that emerges consistently across these different methods is one where the Milky Way and Andromeda are not simply two islands of light separated by empty ocean. They are more like two vast, mostly invisible storm systems, each hundreds of thousands of light-years across, whose outer edges may already be overlapping, with two comparatively tiny, brightly lit centers embedded deep inside each one. Across the whole local group, dark matter is believed to outweigh every star, planet, and gas cloud combined by a factor of roughly 5 to 1. That means the true material shaping the fate of the Milky Way, Andromeda, and everything gravitationally bound to them is overwhelmingly something no telescope has ever directly photographed. Every calculation of the coming merger, every predicted timeline, every simulated what your sky will look like from Earth in a few billion years rests on this same unseen scaffolding. To understand exactly how astronomers calculated the two galaxies' path toward each other, the next part of the account turns to a different kind of measurement entirely, one that had to wait for a space telescope capable of watching Andromeda's position shift by an amount smaller than the width of a human hair held at arm's length, repeated over years. A blueshift, however carefully measured, only reveals motion directly along the line of sight, straightward or away from Earth. It says nothing about motion across the sky, the sideways drift that would reveal whether Andromeda is aimed squarely at the Milky Way or destined to sweep past at a distance. That sideways motion, called proper motion, is astonishingly small for an object 2.5 million light-years away, and for most of the 20th century it was simply too small to measure with any confidence. The breakthrough came from the Hubble Space Telescope, launched into orbit in 1990, partly to avoid the blurring effect of Earth's atmosphere on exactly this kind of precise positional measurement. Starting in 2002 and continuing for roughly 7 years, a team led by the astronomer Roland van der Merel photographed the same small patches of Andromeda repeatedly, tracking the position of individual stars against a fixed backdrop of much more distant background galaxies, objects so far away that their own apparent motion across the sky is effectively zero. Any shift in Andromeda's stars relative to that distant, essentially fixed backdrop had to be Andromeda's own sideways motion. To measure a shift, this small van der Merel's team had to account for and remove several sources of systematic error far larger than the signal itself, including the very slow, predictable wobble of the Hubble Space Telescope's own instruments, and even the tiny apparent shift caused by Earth's own motion around the Sun, a much larger and well-understood effect called parallax that had to be modelled out precisely before Andromeda's own true motion could be isolated. Only after removing every one of these larger, well-understood effects did the small remaining signal, Andromeda's genuine sideways drift, emerge clearly from the data. The shift they found, published in 2012, was tiny almost beyond ordinary description. A drift of a fraction of a thousandth of an arcsecond per year, an angle so small that it would take Andromeda roughly a full human lifetime just to shift its apparent position in the sky by an amount equivalent to the width of a coin held many kilometers away. But over the 7 years of the study, accumulated across thousands of individual stars to average out measurement noise, that drift was real, consistent, and, crucially, small. Andromeda's sideways motion across the sky turned out to be far smaller than its motion directly toward the Milky Way. In other words, Andromeda is not sweeping past us on some grazing arc. It is coming almost straight at us. An arcsecond, for reference, is a unit astronomers use to measure impossibly small angles in the sky. There are 3,600 arcseconds in a single degree, and the full moon, by comparison, spans about 1,800 arcseconds across as seen from Earth. Measuring a shift of a small fraction of a thousandth of an arcsecond per year is roughly equivalent to measuring the width of a human hair from a distance of several kilometers, and doing so reliably enough to trust a conclusion about the fate of two galaxies. Combining that sideways measurement with Slipher's original line-of-sight speed, refined by a century of more precise instruments to roughly 110 kilometers per second, van der Marel's team calculated a most likely outcome. Within the next several billion years, the Milky Way and Andromeda will pass close enough for their gravity to lock them into a long, slow, repeated series of encounters that end, ultimately, in a full merger. Their published estimate placed the first close pass at roughly 4 billion years from now, with the final merger into a single galaxy complete by around 5 to 6 billion years from now, though the exact timeline depends on details of each galaxy's mass and structure that remain difficult to pin down precisely. This finding did more than answer an old question left open by Slipher's discovery a century earlier. It transformed the Milky Way and Andromeda's future from a vague possibility into a specific, dated, physically modelled event one astronomers could now simulate in detail using the two galaxies' measured masses, sizes, and current trajectories. Simulations built on exactly this data, first published in detail by the astronomers Thomas Cox and Abraham Loeb in 2008, and refined many times since, produce a repeated, consistent picture. Two spiral disks of light drawing slowly closer across the dark gap between them, distorting each other's shape more with every pass, before finally settling into one. But even a measurement this careful carries an uncertainty budget, and in a system where the smallest error in angle, projected across millions of years, compounds into a very different outcome, that uncertainty matters enormously. A newer generation of instruments would soon put that uncertainty to the test. The Hubble Space Telescope's proper motion measurement, published in 2012, was a landmark result, but it was not the final word. In 2013, the European Space Agency launched a spacecraft named Gaia, purpose-built to measure the positions, distances, and motions of more than 1 billion stars across the galaxy, with a precision far beyond what any previous instrument could achieve. Gaia's method is called astrometry, the exacting business of measuring exactly where an object sits in the sky and how that position changes, and it does so by observing the same patch of sky repeatedly from an orbit far more stable than any ground-based telescope's view through Earth's shifting atmosphere. Gaia's precision is difficult to overstate. Astronomers have compared its measurement ability to standing on Earth, and being able to detect the width of a human hair held on the surface of the Moon. That level of precision, applied across years of repeated observation, is what allows a sideways drift smaller than a thousandth of an arcsecond to be trusted as real data rather than instrument noise. In 2019, and again in subsequent years using additional Gaia data releases, astronomers recalculated Andromeda's sideways motion with progressively tighter precision. These updates have not overturned the basic 2012 finding, but they have shifted the fine details of the predicted trajectory, and different research groups working from slightly different assumptions about each galaxy's mass distribution have, at times, arrived at somewhat different odds for exactly how direct the eventual encounter will be. This matters because the outcome of a galaxy encounter is exquisitely sensitive to the exact geometry of the approach. Two galaxies aimed directly at each other pass through one another's disks on the first encounter, producing dramatic, immediate distortion. Two galaxies on a slightly offset path might instead swing past each other at a distance, exchanging a strong gravitational tug without a direct pass, looping back around over hundreds of millions of years for a second, closer encounter later. Both scenarios plausibly end in an eventual merger, given enough time and enough repeated passes for orbital energy to bleed away, but they unfold on different timelines and produce different intermediate stages, a difference that matters enormously to anyone trying to model exactly what the sky will look like from Earth at any given point along the way. Adding further complexity, a third galaxy plays a role that early models did not fully account for. The Large Magellanic Cloud, one of the Milky Way's brightest satellite galaxies, carries enough mass of its own to measurably tug on the Milky Way's own motion through space, and its inclusion in newer simulations shifts the calculated trajectory again. One widely reported analysis published in 2025, incorporating updated mass estimates for the Milky Way, Andromeda, and the Large Magellanic Cloud together, suggested the odds of a direct merger within the next 10 billion years could be closer to an even chance than earlier estimates implied, though the researchers behind it were careful to stress that substantial uncertainty remains and that the two galaxies' long-term gravitational entanglement is not in question, only the precise geometry of how it eventually resolves. Part of the reason estimates keep shifting is that a merger prediction this far in the future is built from a chain of separate measurements, each with its own margin of error, each galaxy's total mass, its distribution of mass through the halo, its current velocity in 3 dimensions, and the mass of every significant nearby galaxy whose gravity might tug the trajectory one way or another. Astronomers typically run thousands of separate simulations, each one starting from slightly different, equally plausible values within the measured margins of error, and then look at how the outcomes cluster. When the vast majority of those thousands of simulated futures converge on a similar outcome, an eventual merger, astronomers treat that outcome as robust, even while the fine details, exactly which year, exactly how many passes, remain open to revision as the input measurements improve. None of this means astronomers were wrong, only that they are doing science honestly, refining an answer as better instruments and better models become available, rather than treating an early estimate as beyond revision. What remains solid across every version of the calculation, from Slipher's 1912 blueshift through the most recent reanalysis, is that Andromeda is approaching, that the two galaxies' dark matter halos are either already overlapping, or will be within a relatively short span of cosmic time, and that some kind of gravitational encounter, whether an immediate direct pass or a slower looping series of close approaches, is effectively certain over the next several billion years. What remains genuinely open is only the precise shape and timing of that encounter, not whether the two galaxies are gravitationally entangled with each other at all. For the rest of the account, it is worth holding both possibilities in mind at once: a dramatic direct passage through each other's disks within about 4 billion years, which remains the scenario most simulations still treat as most likely, and a more gradual repeated series of closer and closer encounters stretched across a longer span of time. Either way, the destination is the same. Two spiral disks of light, drawing closer across the dark gap between them, are eventually going to become one. Run the clock forward roughly 4 billion years, to the point most current simulations mark as the beginning of the first close encounter, and the night sky over Earth, assuming anyone or anything remains to look up at it, would already look strange. Long before the two galaxies meet, Andromeda's growth in apparent size accelerates. Tonight, that faint oval smudge spans roughly 6 times the width of the full moon in the sky, though it is so dim that only its bright central core is visible to the naked eye. As the distance closes over the coming billions of years, Andromeda swells, first subtly, then dramatically, eventually filling a large arc of the night sky, its spiral structure and individual bright stars becoming visible without any telescope at all. The first true contact happens not between the two visible disks, but, as earlier chapters established, between the far larger and completely invisible dark matter halos surrounding each galaxy, which likely begin interacting long before the stars themselves draw close. As that invisible interaction strengthens over tens of millions of years, its gravitational effect on each galaxy's outer disk becomes visible in the ordinary starlight astronomers can actually photograph. Long streamers of stars and gas, called tidal tails, are pulled out of each galaxy's outer disk by the other galaxy's gravity, arcing away into space like the trailing edges of two cloaks caught in a shared wind. Simulations built on the measured masses of the two galaxies show these tails stretching for hundreds of thousands of light years, some of the material in them eventually falling back into one galaxy or the other, some escaping into intergalactic space entirely, destined to drift alone for the rest of cosmic history. Triangulum, the local group's third large spiral galaxy, complicates the picture further. Some simulations suggest Triangulum may itself be drawn into a close pass with Andromeda before the main Milky Way encounter even begins, potentially merging with Andromeda first, or alternatively being flung onto a new orbit by the disturbance, before eventually joining whatever galaxy the Milky Way and Andromeda become. Exactly how Triangulum's fate unfolds remains one of the less certain branches of the overall prediction, since its comparatively small mass makes its trajectory more sensitive to small errors in the input measurements than either of the two dominant galaxies. If the two galaxies are indeed headed for something close to the direct pass, most simulations still treat as the likely outcome. The disks themselves pass through one another during the first close approach, sometime around 4 billion years from now. This does not mean the two disks crash together the way solid objects collide. A galaxy's disk is, as earlier chapters established, mostly empty space between widely separated stars, so the stars of one galaxy largely pass through the gaps between the stars of the other. What does interact violently is the gas. Vast interstellar clouds of hydrogen, the raw material from which new stars are born, colliding directly, compressing sharply, and igniting bursts of new star formation far more intense than either galaxy experiences on its own today. This first pass does not immediately produce a merged galaxy. Instead, the mutual gravity between the two galaxies, having interrupted their straight-line approach, pulls each one back toward the other after they swing past, the way two objects connected by an invisible elastic cord snap back together after stretching apart. Simulations show the two galaxies looping past each other several times over the following billion years or so, each pass closer and slower than the last, as orbital energy bleeds away into the surrounding gas, stars, and dark matter through a process called dynamical friction, essentially gravitational drag exerted, as each galaxy's mass disturbs the other's structure on its way past. Each successive pass distorts both galaxies further, stripping away the clean spiral shape both currently have, twisting their arms into elongated, irregular streams of stars. From Earth's surface, assuming the solar system survives this stretch of time in a recognizable form at all, an observer during one of these passes would see two enormous illuminated structures spanning much of the visible sky, their spiral arms visibly disturbed and streaming, bright knots of new star formation glowing pink and blue where the two galaxies' gas clouds are colliding. It would be, by any measure, one of the most dramatic sights the sky could ever offer to an observer on Earth, a sight built entirely from a process that, on the scale of any single human lifetime, produces no visible change at all. The entire sequence, from the first noticeable widening of Andromeda's disk in the sky to the final settled shape the merger eventually produces, unfolds over roughly 2 billion years, a span of time longer than the entire history of complex life on Earth so far. None of this first pass, dramatic as it is, involves two stars actually striking one another. That fact, surprising to most people encountering this account for the first time, comes down to just how much empty space genuinely separates one star from its neighbours, even within a single galaxy's crowded disk. Astronomers can say all of this with reasonable confidence, not because anyone has watched a galaxy merger unfold in real time, an impossibility on any human timescale, but because telescopes across the sky have photographed dozens of other galaxy pairs caught at every different stage of exactly this process, from first contact through final settled remnant, providing a kind of freeze-frame gallery of a single event playing out across the whole visible universe at once. A galaxy's supply of raw star-forming material sits mostly in enormous cold clouds of molecular hydrogen gas, some of them hundreds of light-years across, and containing enough mass to build hundreds of thousands of stars the size of the Sun. Normally, a cloud like this collapses slowly, over millions of years, as gravity within the cloud itself wins out gradually against the outward pressure of the gas, eventually forming a scattered handful of new stars at a time. The Milky Way today forms new stars across its entire disk, at a combined rate of roughly 1 to 2 solar masses worth of material per year, a fairly modest, steady pace that has continued for billions of years. A galaxy collision changes that pace dramatically. When two galaxies pass close enough for their gas clouds to interact directly, the clouds are compressed by the encounter's gravitational tides far faster than they would ever compress on their own, triggering what astronomers call a starburst, a sudden, intense episode of star formation that can, for a period lasting anywhere from a few million to a few tens of millions of years, produce new stars tens or even hundreds of times faster than either galaxy managed before the encounter began. Astronomers have observed exactly this happening in real galaxy collisions elsewhere in the universe, capturing them mid-encounter with rates of new star formation so high that the affected galaxies glow noticeably brighter in infrared light, heated by the sheer number of newly formed, extremely hot young stars embedded in their still dusty birth clouds. Astronomers do not need to imagine what a starburst triggered by galactic interaction looks like, because nearby examples already show it directly. A galaxy called M82, roughly 12 million light-years away, is currently undergoing an intense starburst triggered by a close gravitational encounter with a large neighbouring galaxy, and it glows so brightly in the light given off by hot hydrogen gas and young stars that it is visible even in modest amateur telescopes as an elongated, strikingly bright smear of light, quite unlike the quiet, evenly lit disk of an undisturbed spiral galaxy. For the Milky Way and Andromeda's encounter, current models predict several distinct waves of star formation, one triggered by the initial close pass roughly 4 billion years from now, likely another during a second closer pass some hundreds of millions of years after that, and a final, particularly intense burst during the last stage of the merger itself, when the two galaxies' remaining gas reserves are funneled inward toward the newly combined galaxy's center by the chaotic gravity of the merger in progress. That final burst is expected to be the most dramatic of the sequence, potentially consuming a significant share of both galaxies' remaining gas supply in a relatively short burst, lasting perhaps a few 100 million years, a firestorm of star birth that leaves the newly merged galaxy with far less raw material for future star formation than either galaxy possessed on its own beforehand. This matters for what the merged galaxy eventually looks like, a subject the coming chapters return to directly, because a galaxy's shape and character depend heavily on how much gas it has left to work with. A galaxy still rich in gas keeps forming new stars steadily and tends to maintain a flattened, organized disk, the shape both the Milky Way and Andromeda currently have. A galaxy that has exhausted most of its gas in a short, intense burst, by contrast, tends to settle into a puffier, more disorganized, roughly spherical shape, its remaining stars orbiting on more scattered paths rather than the tidy, shared rotation of a spiral disk. To grasp the scale of one of these bursts, consider that the most massive stars formed in a starburst episode, some many times the mass of the Sun, live extraordinarily short lives by stellar standards, burning through their fuel in only a few million years before ending in a supernova. A violent, explosive death that seeds the surrounding gas with heavier elements forged in the star's core and final explosion. A galaxy undergoing a major starburst can produce enough of these massive, short-lived stars that supernovae occur far more frequently than in a normal, steadily star-forming galaxy, each explosion adding its own burst of energy and enriched material back into the surrounding gas, material that will eventually be recycled into yet another generation of stars. None of this violence touches individual stars directly. It is entirely a story about gas, vast clouds of hydrogen compressed, collapsed, and consumed at a dramatically accelerated pace by the gravitational chaos of two galaxies passing through and around each other. The stars that already exist within each galaxy, including, in this hypothetical future, whatever remains of the Sun and its family of planets, experience this entire firestorm from a comfortable distance. Because stars themselves, it turns out, occupy so little of a galaxy's actual volume that a direct stellar collision during even the most violent stage of a full galaxy merger remains staggeringly unlikely. Exactly how unlikely, and why, is worth explaining properly, because it is the single most counterintuitive fact in the entire story of two galaxies colliding. Every star in a galaxy occupies an almost unimaginably small fraction of the space around it. The Sun, a fairly typical star, has a diameter of about 1.4 million kilometers. Its nearest known stellar neighbor, a system called Alpha Centauri, sits roughly 4.24 light-years away, a distance equal to about 40 trillion kilometers. Divide one number by the other and the Sun's own width is smaller than 1/30 millionth of the distance separating it from its nearest neighbor. A useful way to feel that ratio rather than just read it: shrink the Sun down to the size of a single grain of sand roughly 1 millimeter across. On that same scale, Alpha Centauri, the nearest star to the Sun, would be another grain of sand sitting roughly 30 kilometers away, further than the distance across many entire cities. Now, imagine scattering hundreds of billions of these sand grains through a volume of space, roughly 100,000 light-years wide, each one drifting along its own independent orbit around the galaxy's center, and ask how often two of them might actually collide. Astronomers have run exactly this calculation for the coming Milky Way and Andromeda merger, using the measured density of stars in each galaxy's disk and each galaxy's total star count, and the answer comes back close to zero. Even during the most violent stage of the merger, with two galaxies' worth of stars passing directly through the same volume of space, the expected number of direct star-on-star collisions across the entire event is vanishingly small, likely fewer than one collision total, out of a combined stellar population exceeding 1 trillion stars. Near the Sun's own position in the Milky Way's disk, the average spacing between stars works out to roughly one star for every few hundred cubic light-years of space, a density so low that if every star in that volume were shrunk to the size of a beach ball, the nearest other beach ball would still sit many kilometers away in every direction. Multiply that same low density across the combined stellar population of two colliding galaxies, and the odds of any two of those beach balls actually touching, even during the most crowded moments of the merger, remain close to nothing. This is the detail that most surprises people encountering the Andromeda account for the first time, because a galaxy collision sounds, by name alone, like it should be a catastrophe of stellar impacts, stars smashing into each other by the billion. The reality is closer to two enormous, extremely sparse swarms of sand grains, each grain separated from its neighbours by tens of kilometres on the shrunk-down scale above, passing through one another. Almost every star involved will simply continue along a newly bent orbital path, its motion reshaped by the combined gravity of the merging galaxies, without ever coming remotely close to physically striking another star. What does happen to individual stars, even without any direct collision, is a significant rearrangement of their orbits. As the two galaxies' gravity tangles together during the encounter, a star that spent its entire previous history orbiting calmly within the Milky Way's disk may find its orbit stretched, tilted, or flung outward into a far looser, more scattered path around the newly forming combined galaxy. Simulations built for the eventual Milky Way and Andromeda merger suggest the solar system itself, along with the rest of the Sun's immediate stellar neighbourhood, has a reasonable chance of being displaced considerably from its current position, potentially ending up much farther from the newly merged galaxy centre than it sits today, though the exact outcome for any single star, including the Sun, cannot be predicted with certainty this far in advance. It is even possible, current simulations suggest, that at some point during the encounter the solar system could be temporarily flung into Andromeda's outer disk, or Andromeda's stars could sweep past close enough to appear as a dramatically dense field of new stars in Earth's sky, before gravity eventually settles both stellar populations into the newly formed galaxy's calmer final structure. This same basic fact, that individual stars almost never collide even when their parent galaxies fully merge, holds true for essentially every galaxy merger astronomers have ever studied, and it follows directly from just how much empty space exists inside what looks, from any distance, like a solid disk of light. A galaxy is not a solid object being thrown at another solid object. It is closer to two very thin, very widely spaced clouds of individually moving points passing through the same general region of space, at speeds and separations that make actual contact between any two of those points a matter of extraordinary, almost impossible coincidence. Gas clouds, unlike stars, are not points. They are diffuse, extended structures that fill a meaningful fraction of the space around them, which is exactly why gas, not stars, is where nearly all of the encounter's visible drama actually happens, as the previous chapter described. Stars pass through each other's company largely undisturbed. It is the space between them, and the small fraction of that space occupied by drifting gas, where a galaxy collision actually does its work. At the exact centre of the Milky Way sits an object astronomers call Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of the Sun, confirmed directly in 2020 through decades of tracking the orbits of stars swinging closely around it, an achievement that earned that year's Nobel Prize in Physics for the astronomers who led the effort. A black hole, for anyone unfamiliar with the term, is a region where mass has been compressed so densely that its gravity prevents even light from escaping past a boundary called the event horizon. Importantly, a black hole's gravity beyond that boundary behaves exactly like the gravity of any other object of the same mass. It does not reach out and pull in matter from a distance any more aggressively than an ordinary star of equal mass would. The stars currently orbiting Sagittarius A star do so in stable, predictable paths, the same way planets orbit the Sun. Direct visual evidence that black holes exist at all arrived in 2019, when the Event Horizon Telescope, a global network of radio observatories working together as a single instrument the size of the Earth, produced the first image of a black hole's silhouette, capturing the supermassive black hole at the centre of a distant galaxy called M87, outlined against the glowing, superheated gas swirling just outside its event horizon. That image, and a similar one of the Milky Way's own Sagittarius A star released in 2022, turned what had been an entirely theoretical prediction of Einstein's equations into a directly photographed object. Andromeda hosts a central black hole of its own, considerably more massive than the Milky Way's, with estimates placing it at somewhere around 100 million times the mass of the Sun, based on the motion of stars and gas clustered near Andromeda's center. When the two galaxies eventually merge into one, these two black holes will not remain separate forever. Each currently sits at the gravitational center of its own galaxy, and as the merger progresses and the two galaxies' stars and gas settle into a single shared structure, both black holes will sink gradually toward the center of that new combined structure, dragged inward over hundreds of millions of years by dynamical friction, the same gravitational drag process described earlier, here acting on an object massive enough to visibly disturb the stars and gas around it as it moves. Once both black holes arrive near the new galactic center, they will begin orbiting one another as a bound pair, spiraling closer over time as they continue to lose orbital energy, first to dynamical friction against the surrounding stars, and eventually, once close enough, to the emission of gravitational waves, ripples in space itself produced by the acceleration of extremely massive objects, a prediction of Einstein's general theory of relativity. That prediction was confirmed directly when two much smaller black holes were detected colliding in a distant galaxy, a signal recorded by the Laser Interferometer Gravitational Wave Observatory, known as LIGO, in September of 2015 and announced publicly the following February. That detection, and dozens of similar ones recorded since, gave astronomers direct observational confidence that black holes really do merge this way, providing the physical basis for predicting the same eventual fate for the Milky Way's and Andromeda's central black holes. The final merger of the two supermassive black holes, once they finally spiral together, is expected to happen long after the surrounding galaxies have already settled into their new combined shape, likely on the order of billions of years after the stellar merger itself completes, since a supermassive black hole pair can spend an extremely long time in a slow, gradually tightening orbit before the final rapid plunge. The resulting single black hole, formed from the combined mass of both progenitors, would likely settle at the center of the newly merged galaxy, with a total mass in the range of 100 million or more solar masses, dwarfing either original black hole individually. None of this poses any direct threat to anything orbiting at a safe distance, in the same way that neither black hole poses a threat today to the stars currently orbiting each one safely. A supermassive black hole's dramatic reputation, the idea that it reaches out and devours everything nearby, is one of the most persistent misconceptions in popular science writing about black holes. What actually determines whether an object falls into a black hole is the same basic orbital mechanics that determines whether a planet falls into its star. An object with a stable orbit at a safe distance stays in that orbit indefinitely, black hole or ordinary star, unless some outside force disturbs it. What the eventual black hole merger will produce, according to current models, is one final, brief, and extraordinarily energetic event, a burst of gravitational waves far stronger than anything LIGO has yet detected from smaller stellar mass black hole mergers, a ripple in space-time itself spreading outward at the speed of light from the newly merged galaxy's center carrying away, in that final instant, an amount of energy equivalent to a meaningful fraction of the combined black hole's total mass converted directly into the fabric of space itself according to Einstein's famous equivalence between mass and energy. It would be, by any measure, one of the most energetic single events in the entire multi-billion-year story of the Milky Way and Andromeda's merger, and it would happen essentially unnoticed by any star or planet still orbiting safely nearby. Once the stellar merger between the Milky Way and Andromeda is complete, likely somewhere between 5 and 7 billion years from now, depending on which trajectory the two galaxies actually follow, the result will not resemble either original galaxy. Both the Milky Way and Andromeda today are spiral galaxies, flattened rotating disks with organized arms winding around a central bulge, a shape that depends on stars and gas moving together in roughly the same orbital direction, in roughly the same plane. A major merger between two galaxies of comparable mass, sometimes called a major merger to distinguish it from smaller galaxies being absorbed by a much larger one, tends to destroy that organized structure entirely. During the chaotic middle stages of the merger, stars from each original galaxy end up on orbits that no longer share a common plane or a common rotational direction, scattered instead into a wide range of orbital angles by the tangled, shifting gravity of the merging system. The result, once the system finally settles into a stable configuration, is a roughly spherical or egg-shaped galaxy called an elliptical galaxy, its stars orbiting the shared center on a scattered range of paths, more like bees swarming a hive than the disciplined single-direction rotation of a spiral disk. Astronomers already have a nickname for this predicted future merger remnant, Milkomeda, or sometimes Milkomeda, combining the two current galaxy names into one, though no formal name will matter to anyone until it actually exists. This predicted transformation is not a guess based on the Milky Way and Andromeda alone. Ellipticals are common throughout the observable universe, and a large body of evidence, built from decades of study, connects them directly to past merger events. Elliptical galaxies typically contain older, redder stellar populations, tend to have used up most of their gas already, and often show subtle structural features, faint shells and ripples of stars in their outskirts, that match exactly what simulations predict a settled merger remnant should look like generations after the event itself. Many of the largest galaxies known, including the giant elliptical galaxies found at the centers of massive galaxy clusters, are believed to have grown to their current size specifically through repeated mergers with smaller galaxies over billions of years. The giant elliptical galaxy at the center of the nearby Virgo cluster, the same M87 imaged by the Event Horizon Telescope, is thought to have grown to its current enormous size, roughly 1,000 times the mass of the Milky Way, through exactly this kind of repeated galaxy stretched across billions of years, making it a useful, if far larger, preview of the kind of galaxy Milkomeda might eventually resemble, at a much smaller scale. Once the final starburst described earlier consumes most of the newly merged galaxy's remaining gas, the rate of new star formation drops sharply, since there is little raw material left to build new stars from. Astronomers describe this kind of galaxy, one that has largely stopped forming new stars and is dominated by an aging population of longer-lived, cooler, redder stars, using the slightly informal shorthand red and dead, a description that current models suggest will eventually apply to Milkomeda as well, likely within a few billion years of the final merger completing. That does not mean Milkomeda will be a lifeless void of light. A galaxy the combined mass of the Milky Way and Andromeda together will still contain well over 1 trillion stars, and star formation, while sharply reduced, is unlikely to stop entirely for a very long time, since even a mostly quiet elliptical galaxy retains some scattered pockets of gas capable of forming occasional new stars over the following billions of years. What changes is the character of the galaxy. From two actively star-forming spiral disks, each still building new stars at a steady, modest pace today, to one much larger, much quieter elliptical structure, its bright era of vigorous star formation mostly behind it, its remaining stars slowly aging and dimming together over the following tens of billions of years. This transformation from spiral to elliptical is one of the most well-studied processes in galactic astronomy, precisely because it is not unique to the Milky Way and Andromeda's particular future. It is, current evidence strongly suggests, a routine and recurring stage in how the largest galaxies in the universe grow and evolve, one that the Milky Way and Andromeda are simply about to experience for themselves, joining a long line of galaxy pairs across the observable universe, already caught somewhere in the middle of exactly the same process. Everything described so far unfolds across a timescale where the Sun itself is not a fixed, unchanging backdrop. The Sun, like every star, is presently in the middle of its own independent life cycle, fusing hydrogen into helium in its core, a process that has powered it steadily for roughly 4.6 billion years, and, according to current stellar models, will continue for roughly another 5 billion years before the Sun's core hydrogen finally runs low. When that happens, the Sun will begin a transformation of its own, swelling into what astronomers call a red giant, its outer layers expanding dramatically, likely engulfing Mercury and Venus and rendering Earth almost certainly uninhabitable long before the Milky Way and Andromeda merger reaches its most dramatic stages. This matters for the Andromeda account because it means the two timelines run roughly in parallel, not sequentially. The Milky Way and Andromeda's first close pass, at roughly 4 billion years from now, arrives close to, or perhaps even before, the point where the Sun's own life cycle begins its dramatic final act, depending on exactly which estimate for each timeline turns out to be most accurate. Whatever remains of the solar system by the time the galaxy merger is in full swing, whether a swollen red giant sun with whatever planets remain intact, or the eventual smaller, dense stellar remnant called a white dwarf that a star like the Sun leaves behind after shedding its outer layers, will be swept along by the same gravitational reshuffling affecting, every other star in both galaxies. A white dwarf, the compact stellar remnant a star like the Sun eventually leaves behind, packs roughly the Sun's entire remaining mass into a sphere only about the size of Earth, and it no longer generates any new energy through fusion, instead cooling slowly, over trillions of years, from the residual heat left over from the star's earlier life. Whatever the Sun eventually becomes will still be gravitationally bound to whatever remains of its planetary system, carried along together through every stage of the coming galactic merger. As earlier chapters established, the odds of the Sun, or its remnant being involved in any direct stellar collision during the merger, remain extraordinarily low, for exactly the same reason that applies to every other star in either galaxy: the enormous distances separating individual stars, even during the most crowded stage of a full galaxy merger. What is far more likely, based on current simulations, is that the Sun's orbital position within the newly forming combined galaxy will shift substantially, potentially moving it much farther from the galactic center than its current position, roughly 2/3 of the way out from the Milky Way's center today. Some simulations suggest a modest chance the solar system could even be temporarily captured by Andromeda's gravity during one of the earlier close passes, before eventually settling into an orbit within whatever galaxy the two eventually become, though this remains one of the least certain details in the entire predicted sequence, given how sensitively it depends on the exact geometry of an encounter that has not happened yet. It is worth being clear about what this means for any hypothetical observer on Earth, purely as a thought exercise, since the planet itself is expected to be uninhabitable long before any of the merger's most dramatic stages occur, for reasons entirely unrelated to Andromeda. The Sun's own gradual brightening over the coming billion years, an ordinary consequence of stellar aging that has nothing to do with the galaxy merger at all, is expected to raise Earth's surface temperature enough to boil away its oceans within roughly the next 1 to 2 billion years, long before the first close pass with Andromeda even arrives. Whatever fate ultimately awaits the Earth, the Andromeda merger is very unlikely to be the deciding factor. That distinction matters for keeping this whole account honest. It is easy to fold the Sun's eventual transformation and the coming galaxy merger into a single dramatic narrative, but they are two largely independent processes that happen to unfold across roughly the same span of cosmic time, one governed by the internal physics of how an ordinary star like the Sun ages, and the other governed by the external gravitational choreography of two galaxies drawing together. The Sun would face its own transformation into a red giant on essentially the same schedule whether Andromeda existed at all. Andromeda's arrival adds a second, entirely separate layer of change on top of a solar system already destined for a dramatic transformation of its own, for reasons that trace back to the Sun's own core, rather than to anything happening 2.5 million light-years away. Predicting an event billions of years in the future, one no human will ever witness directly, might seem like an exercise in pure speculation. It is not, because the universe offers something almost as good as a time machine, an enormous number of other galaxy pairs scattered across the observable universe at every possible stage of exactly this same process, each one effectively frozen at a different moment along a timeline. The Milky Way and Andromeda have not yet begun. The antennae galaxies, a pair catalogued as NGC 4038 and NGC 4039, sit roughly 45 million light-years from Earth and are caught by cosmic standards in the early to middle stages of a direct collision very similar to the one predicted for the Milky Way and Andromeda. Photographs made using the Hubble Space Telescope show two long, curving tidal tails of stars stretching away from the main bodies of the two galaxies, exactly the kind of structure earlier chapters described being pulled out of a galaxy's disk by the gravity of a close encounter, along with brilliant clusters of newly formed stars glowing where the two galaxies' gas clouds have collided and triggered a starburst. The antennae are, in effect, a live photograph of a stage the Milky Way and Andromeda are still several billion years away from reaching. Other pairs capture different moments. A system known informally as the Mice galaxies, catalogued as NGC 4676, shows two long, straight tidal tails stretching from each galaxy in a shape that gave the pair its nickname, caught at an earlier stage of interaction than the antennae, its two disks still largely intact but already visibly disturbed by their mutual gravity. At the far end of the process sits a galaxy called ARP 220, roughly 250 million light-years away, believed to be the settled or nearly settled remnant of a merger, Between two spiral galaxies that began interacting tens of millions of years ago, its center now glowing intensely in infrared light from an extraordinarily concentrated burst of ongoing star formation, thought to be the same kind of final starburst that current models predict will eventually consume much of the Milky Way and Andromeda's remaining gas. More recently, the James Webb Space Telescope, launched in 2021, has photographed numerous merging galaxy pairs at even greater distances and in far greater infrared detail than Hubble could achieve, resolving individual clusters of newly formed stars within the tangled gas of galaxies caught mid-collision, providing an increasingly detailed catalogue of exactly how gas behaves, how tidal tails form, and how a starburst unfolds across many different examples of essentially the same underlying physical process. Every one of these observed systems gives astronomers another data point against which to test and refine the same computer simulations used to predict the Milky Way and Andromeda's own future. Beyond individual famous pairs, wide sky surveys have now catalogued thousands of interacting and merging galaxies at every stage of the process, spanning distances from a few million to many billions of light-years away, effectively allowing astronomers to assemble a single continuous timeline of galactic merging by sorting these thousands of individual snapshots by how far along each pair appears to be. This is how astronomers can speak with genuine confidence about an event so far in the future. Not because any single simulation is perfectly precise, but because the physics behind it, gravity acting between two extended gas-rich stellar systems, has been tested and observed directly, over and over, in dozens of real galaxy pairs at every stage of the process, from galaxies just beginning to feel each other's gravitational pull to fully settled elliptical remnants that finished merging long ago. The predicted future of the Milky Way and Andromeda is not an isolated guess. It is one more entry in a well-established, richly observed category of event that happens to galaxies of this general size and gas content throughout the universe, on a schedule set entirely by their mass, their gas content, and the geometry of their approach. What makes the Milky Way and Andromeda's case unusual is only that it happens to be, of all the mergers now visible anywhere in the sky, the one happening to us. Step back from every individual detail: the blueshift Vesto Slipher, measured in 1912, the sideways creep the Hubble Space Telescope detected a century later, the Gaia refinements, the tidal tails, the starbursts, the slow sinking of two supermassive black holes toward a shared center, and a single simple fact remains at the center of the whole account. Gravity, acting patiently across 2.5 million light-years and several billion years, is going to take two separate galaxies, each containing hundreds of billions of stars, and make them one. Nothing about this process required any dramatic, sudden violence on the scale it might first suggest. It required only ordinary physics, given enough time to work. That patience is, in fact, the real lesson the Andromeda account offers. Every process described in the preceding chapters, from the first tiny sideways drift too small to detect for most of the 20th century, to the eventual merger of two black holes each many millions of times the Sun's mass, unfolds on a timescale that makes a single human lifetime, or even the entire recorded history of human civilization, look instantaneous by comparison. The universe is not static. Structures that appear permanent and unchanging within any observable stretch of time, two separate spiral galaxies, a stable orbit, a star quietly fusing hydrogen in its core, are all on a long enough timescale, in motion towards some further transformation. The Milky Way looks fixed and eternal, only because 4 billion years is far longer than any process capable of observing it. Consider what 4 billion years actually spans. It is longer than the entire history of life on Earth, longer than the time since the first single-celled organisms appeared in ancient oceans, roughly comparable to the age of the Earth itself. The Milky Way and Andromeda's first close pass sits that far in the future, and the final settled elliptical galaxy that eventually results lies further still, past a horizon of time long enough that predicting exactly what, if anything, will exist to observe it is itself a matter of open speculation rather than settled science. What is not speculation is the gravitational calculation itself, tested and retested against a century of steadily improving measurement, from a single blueshift recorded on a photographic plate in 1912 to a spacecraft mapping the sky star by star more than a century later. It is also worth returning one final time to what this coming merger will not do. It will not destroy the Milky Way's stars in some catastrophic wave of stellar collisions. It will not, most likely, threaten the Earth directly, whose fate is sealed on a separate and largely unrelated timeline by the Sun's own gradual aging. It will not involve any black hole reaching out to devour anything beyond its own immediate, extremely small event horizon. Nearly every dramatic, catastrophic image the phrase galaxy collision might conjure turns out, on close examination, to be wrong, replaced by a slower, stranger, more genuinely remarkable picture. Two vast, mostly empty structures, each barely disturbed at the level of any individual star, gradually reorganizing themselves around each other's gravity into something new, while the handful of things that actually do interact violently, clouds of gas, tidal tails, the slow sinking of two central black holes, do so almost entirely without touching a single star directly. The Milky Way and Andromeda are not unusual for doing this. Every large galaxy visible in the sky today, including the giant ellipticals at the center of the largest galaxy clusters, likely grew to its current size through some version of the same process, one merger after another, stretched across billions of years, each one leaving faint structural fingerprints, shells and ripples of displaced stars, still visible today to a sufficiently careful telescope. Andromeda's approach is not a special threat aimed at the Milky Way. It is the Milky Way's turn to take part in one of the most ordinary processes in galactic evolution, one that has already happened, and is still happening, to countless other galaxies across the observable universe. What Milkomeda eventually becomes, an aging elliptical galaxy, its spiral structure gone, its two supermassive black holes eventually merged into one, its stars orbiting on scattered paths around a shared center, will itself be only one further stage in an ongoing account. The universe's overall expansion, which earlier chapters distinguished carefully from the local group's own internal gravity, will continue carrying every other galaxy cluster farther away, meaning that whatever the merged galaxy's night sky eventually looks like, it will very likely show fewer neighboring galaxies than the Milky Way's sky shows today, more of the surrounding universe having drifted beyond the reach of its light. Locally, gravity binds, on the largest scales expansion wins. The Andromeda merger is a story about the boundary between those two forces, playing out right now at a pace too slow for any single human observation to catch. Nothing about this outcome required intention or design. It required only mass, distance, and time, the same three ingredients responsible for every structure gravity has ever built, from a single star collapsing out of a cloud of gas to a supermassive black hole slowly gathering the stars around it into a stable orbit. Tonight, the faint smudge of light in the constellation Andromeda looks exactly as it has looked for as long as any human has been alive to see it, a quiet, unmoving point in a dark sky. It is not unmoving. It is falling toward the Milky Way at more than 100 kilometers every second. Its light still compressed slightly toward blue, exactly as Vesto Slipher measured it more than a century ago, carrying the same simple, patient message it has carried the entire time. Two galaxies, each home to hundreds of billions of stars, are drawing steadily closer, on a timescale vast enough that neither one will ever visibly move in the sky of anyone alive to look up at it, and inevitable enough that, given a few more billion years, they will not remain two galaxies at all. The Milky Way and Andromeda's coming merger is, in the end, a story about how much can change on a timescale too long for any single observation to register directly, and about how much confidence careful measurement can still produce about events no one will ever witness. A blueshift recorded in 1912, refined by a space telescope watching for a decade, refined again by a spacecraft measuring the sky with a precision equivalent to spotting a coin from thousands of kilometers away, has turned an ordinary-looking smudge of light into a dated, physically modelled future, a first close pass roughly 4 billion years from now, a slow sequence of tidal tails and starbursts, the eventual sinking and merging of two supermassive black holes, and finally, a single, quieter elliptical galaxy where two spiral disks once turned separately. Almost none of it will involve two stars ever touching. Nearly all of it happens in the vast, mostly empty space between stars, in clouds of gas compressing into new light, and in the slow pull of dark matter halos that reach out far beyond anything a photograph can show. The Sun's own fate, tied to its own internal fusion clock, will likely arrive first regardless. What remains constant across every version of this story is the simple fact that started it. Two galaxies, each carrying hundreds of billions of stars, are approaching each other tonight, patiently, at more than 100 kilometers every second, exactly as they have been since long before anything alive on Earth could measure it.